Hello and welcome to the fifth of the lectures in this week 7 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In the previous lecture, we had looked at building a Mamdani fuzzy inference system using the fuzzy logic toolbox available in MATLAB to approximate a given function. Now, at that time, we were wondering, is there any need to build a fuzzy inference system to approximate a function that is already known? Well, firstly, it's a proof of concept that we can build a Mamdani fuzzy inference system to approximate a given function. Of course, it is theoretically known that any given continuous function can be approximated to arbitrary accuracy using a Mamdani fuzzy inference system with appropriate choice of inference operators. Secondly, a system function is not known to us. However, some qualitative properties of the system function may be known to us. Perhaps we might know that it's an oscillatory function, or it might be a monotonic function, or we might know about its behavior in different subdomains, or we might know the bandwidth within which the graph of the function might lie. So using these heuristics, we can construct a fuzzy inference system to approximate the system function. In this lecture, we will see one practical application among the many in which fuzzy inference systems are employed and found use. In this lecture, we will take a simple application of contrast enhancement in images. A common method that is used, especially in the case of grayscale images, is that of histogram equalization. We will look at histogram equalization as a kind of a monotonic transformation of the dynamic range of a given picture, grayscale image. Seeing it as a monotonic transformation, as a system function which is being monotone, we will try to simulate this using a fuzzy inference system. We will compare the results. In fact, we will go one step further. Having seen it as a monotonic transformation, we might also be able to come up with further improvisation of the original fuzzy inference system and see the results that we obtain. Now, let's look at the following images. If we were to look at these four images and ask which of them has visual quality appeal, clearly the one at the right bottom trumps everything else. If you wonder why, the one on the leftmost on top, you see that it's largely dark. The one on the top right it seems as if it is overexposed, and the one on the bottom left is somewhere in the mid-range, and clearly the one at the bottom right is quite clear. It's as if for the other three images there is a filter that is kept on top of it, perhaps a translucent sheet or a glass. Now the thing is, the contrast in these images is actually very less. What do we mean by the contrast? The pixel intensities of these images, they occupy a very less range. The dynamic range of the pixel intensities of the three pictures, which we feel does not have the visual quality appeal, is actually very, very less. Now, what is histogram equalization? If you plot the histogram of pixel intensity values, the shape and position of this histogram offers useful information about the contrast in the picture, and hence this can be used to perform contrast enhancement. Let's look at the same pictures. If you look at this dark image, slightly darker image, and look at the histogram of the pixel intensities present in this picture, we see that it's largely towards the darker end of the spectrum. So on the x-axis, we have the pixel intensities. This is a grayscale image, so we have normalized it between 0 to 255. And these are the corresponding pixel intensities, once again, which are normalized based on the number of points in the image. So this bar here represents that the number of pixels with pixel intensity 50 is almost 4% of the entire image. Now if you look at it for this image, where we felt largely the pixels are somewhere in the middle range, neither black nor white, the histogram of pixel intensities also confirms this, that they are in around the middle of the range, and you see that they are not well spread. So the dynamic range, both in terms of its width, the spread, and also in terms of the position, they are actually placed in the middle. Now let's look at some actual pictures. If you look at this image of a car, we see that the spectrum, the histogram, which could occupy the entire 0 to 255 interval, is actually restricted to between 100 to 200. And in this case, once again, what looks like some kind of a blurry image, if you look at the dynamic range of the pixel intensities, which is again is restricted, it is not the entire interval between 0 and 255. So is the case with this image. If you look at this image, we believe that the details are quite good in this, and if you look at the corresponding spectrum, the histogram of the pixel intensities, we see that its dynamic range is quite high. It occupies quite an amount of the interval 0 to 255. Now, the idea behind histogram equalization is this. Once again, let us look at the images that we began with. So a darker image, its histogram of pixel intensities is closer to the lower end of the boundary, 0 to 255 interval. The grayish image somewhere in the middle, and the almost overexposed image towards the higher end of the 0 to 255 interval. However, what we may be interested in is not only the position but also the spread. If you look at these images, their positioning wise, they are either close to the lower end of the interval or in the middle or in higher end of the interval. However, their spread is quite limited. Now look at this image, which we felt was quite a good quality in terms of visual appeal. If you look at the corresponding histogram of pixel intensities, we see that it's quite well spread, almost occupying the entire 0 to 255 interval. So taking cue from this, given a pixel, an image, we look at the corresponding histogram of pixel intensities. Let's assume this is the histogram of pixel intensities for a given image. We find the dynamic range of this histogram. By the dynamic range, we actually mean the values, the pixel intensity values that are actually assumed in the image. So this is the dynamic minimum and this is the dynamic maximum. And what we do is, after finding the dynamic range of these pixel intensities, we essentially stretch it monotonically from this dynamic range to the entire 0 to 255 interval. Histogram equalization essentially does this monotonic transformation of this dynamic range of a picture to the entire 0 to 255 interval. So visually, this is exactly what it does. Now let's look at the results of applying histogram equalization to some of the pictures that we have seen. So for this picture, we have seen that it is of low contrast, and this is the corresponding histogram of pixel intensities. This is the histogram equalized image. Already you can see the quality has improved. We are able to make out some details in the image. And if you look at the corresponding histogram of pixel intensities, it is quite well spread. You might notice that there are a lot of pixels almost at the white end of the spectrum, and those are again retained. So the dynamic range of the modified or the histogram equalized image is essentially the entire 0 to 255 interval. And for this image having these scars, This is the original histogram of pixel intensities of the corresponding original image that we consider. And you see that this is the histogram equalized image. Already you can see details in greater depth. And if you look at the corresponding histogram of pixel intensities, we see that the dynamic range has actually expanded. For this picture, once again, what we have is this is the histogram of pixel intensities. The dynamic range is much better than earlier, but it could be even greater. Histogram equalization does that, wherein you see greater detail in the images. Now, having seen histogram equalization as a monotonic transformation from the dynamic range to the entire 0 to 255 interval, we understand this is the system function that we want to capture. Now the question is, can we capture this by a Mamdani fuzzy inference system? And let's see what it means to build a Mamdani fuzzy inference system to capture this idea. Now, we may not be implementing histogram equalization exactly, but we have taken the idea from here that it is essentially increasing the dynamic range of pixel intensities contained in the picture. And can we implement this monotonic transformation using a fuzzy inference system? That is what we will look into presently. What does it mean to implement such a fuzzy inference system? Well, we know that a Mamdani fuzzy inference system, which is a similarity based reasoning system, to implement that means specifying all these things. We need to specify the fuzzy covers on the input and output domains, build the rule base where the antecedents and consequence come from the corresponding fuzzy coverings on x and y, and choose the corresponding operators: a fuzzification, a matching function, a modification function, an aggregation function, and finally a defuzzifier. We know that in this case we need to implement a monotonic transform from the dynamic range dm to the entire 0 to 255 interval. It would also be helpful if it were an onto function, so that we really increase the dynamic range to the entire interval of 0 to 255. So it means to determine the dynamic range, the endpoints of the dynamic range, and find fuzzy covers, determine the fuzzy covers on the input domain, which for us is the dynamic range, the interval dm, and the output, which is essentially the entire interval 0 to 255. Now, how do we do this? Earlier, we used histogram equalization to stretch it from the dynamic range to the entire 0 to 255 interval, expand the dynamic range. In our case now, what we will do is take the input dynamic range, this interval, and build n fuzzy sets on it. Similarly, we will find n fuzzy sets on the entire interval of 0 to 255 and relate each of these fuzzy sets on the input domain to the output domain as rules, and use these rules, the rule base that's constructed this way, in the Mamdani fuzzy inference system to approximate or to come up with this dynamic range expansion. How do we do this? Let's look at a particular MATLAB implementation of this idea. Well, let us look at one particular implementation of the idea that we just discussed. Let us consider the image of the cars that we have seen. There is the corresponding histogram of pixel intensities. Let us apply histogram equalization on this. Now, before that, notice here that the dynamic min and dynamic max of this histogram of pixel intensities is essentially 97 and 243. Well, looking at the figure, we see that essentially it is around 200 or so, but there are also some pixel intensities, pixels taking the value 243. So this is the data that we have got from the histogram of pixel intensities. Now let's apply the histogram equalization on this image. We have seen this image, which shows much more detail about of what is there in the picture, and what we have here is essentially the monotonic transformation that the histogram equalization has performed on this image or on the pixel intensities of this image. You will see once again that around 40% of 0 to 255, of course these are the x and y axes are normalized. So 0 to 255 is mapped to 0 to 1 on both x and y axis. So around 97 would imply around 40%, 0.4 on this axis, and you see here around 200 is essentially around 80% or 0.8 on this axis. We see that before 0.4 up to 97 it is almost 0, and above 200 or so it is almost 1. That means we have extended, pulled the dynamic range from 97 or 200 plus to essentially entire 0 to 255, and we see that it is increasing monotonically. That means any pixel intensity value between 97 and 200 is going to be mapped in an increasing way. So you see here that a pixel value of 97 is perhaps mapped only to a pixel value of 25, but the effective range has been increased, and so the contrast that is present in the image is actually getting better. Now, so these are the two values that we want, 97 and 243, and using this we will build our fuzzy inference system. So now that we have the dynamic range, which is the interval 97 to 243, this constitutes the input domain X for us. Next, the Y domain, the output range is already fixed. It's between 0 to 255. That's how much we would like to expand this X into. The question now is how to find the fuzzy covering on this. We will take n equispaced intervals on both the dynamic range X and also on the entire 0 to 255 interval, and using these equispaced points we will build our fuzzy covering. In this particular implementation, what we have coded here is to use triangular fuzzy membership functions both on the input and the output domains. So you see the input partition consisting of 21 such fuzzy sets. We have taken 20 equispaced points between 97 and 43. So we've got 21 fuzzy membership functions, which are triangular membership functions. These will form the 21 antecedents on X, and similarly the output space has also been partitioned into using 21 triangular membership functions. Now, using these values as the L, C and R, the left, center and the right point for the triangular membership function, we can build a fuzzy inference system. Allow me to show you the actual fuzzy inference system that we have built. So we see here that when we are using a Mamdani fuzzy inference system, implementing it in the fuzzy logic toolbox using MATLAB, the H by default is fixed as a singleton fuzzification. We have this AND and OR method combined together to give us the matching function. For the modification, which is shown here as implication, we have taken product. For the aggregation, the sum, which is essentially the Ukashevich-Tycho norm, and for defuzzification we are using centroid defuzzifier. Let's look at how the input fuzzy sets are. So now this is the fuzzy covering that we have on the X domain. You will see here we have mapped it from 0 to 255. However, effectively it is between 97 and 243, and these are the 21 membership functions which form the fuzzy covering on the interval 0 to 255. Once we have fixed up the number of output membership functions, then on 0 to 255 using triangular fuzzy sets, it is straightforward. These are the membership functions that we are going to have, and all we now need to do is fix up the rules. The way we have created the fuzzy coverings, it was clear that we are going to map A1 to B1 and so on. So, and that is what we see here. So you see here there are these 21 rules, 21 fuzzy sets on the input domain and 21 fuzzy sets on the output domain which are related. Now let's give some values here and see. So if you, for this fuzzy system, if you give a pixel intensity value of say 5, what we expected, it should be 0, but it is somewhere very close to 0, 3.5. And if you give say 15, once again it is 3.5. If you give 50, once again it is 3.4, slightly moved up perhaps. In fact, it can be checked up to 96, it remains at 3.4, which is very close to 0. Now from 97 onwards, it starts to move up. So till 97, it is 3.4. If you put 98, you see already it is moving to 5.36. So if you give 120, it has gone up to 40. If you give 180, it has gone up to 145. So essentially we are stretching it. Between 97 and 243, we are going to stretch it. Let's look at what value 240 takes. We see it has gone up to 247. If you go to say 245, it has gone to 252. So it is very close to 255, which is the higher end of the spectrum between over the interval 0 to 255. After that, almost it remains a constant, whether you take 250 or not. This is how it is. Now let's look at the surface, the function that it is trying to map. You see here, up to 97 it is almost 0, and up to 243 or so it is coming very close to 250, and it almost remains the same or slightly monotonic there. So this is the system function that we have captured using our fuzzy inference system. So once again, we had the idea that to be able to stretch the dynamic range, we need a monotonic function whose domain is the actual dynamic range of the given input image, which needs to be stretched to the entire 0 to 255 interval, which becomes our output domain y. And how we did it was finding the dynamic range, partitioning it, finding a fuzzy covering on both x and y, and relating them as antecedents and consequence in rules, and using the Mamdani fuzzy inference system. Well, now let's look at what exactly we get if we apply this fuzzy inference system on the original image. So remember, the original image can be looked at as a matrix of pixel intensity values. So we take the image and give each of these pixel intensity values at each of these positions and find out what is the output pixel intensity value given by our fuzzy inference system, and map that as an image. Map an image with pixel intensity values corresponding to the output of the fuzzy inference system. If we do that, this is what we get. This is the original image. This is the histogram equalized image, and what we see here is actually the image that we would get if you employ the Mamdani fuzzy inference system that you have just built. Let's look at each of these figures in comparison, also along with their histograms of pixel intensities. Well, this is the image that we began with, and we know this is the corresponding histogram of pixel intensity. The histogram equalized image is given in the bottom left, and this is the image we obtain when we apply the Mamdani fuzzy inference system that we have built, wherein we have only taken the qualitative nature of the transformation that we want, that is essentially monotonic, and we wanted to expand the dynamic range of the image. When we see here, comparatively speaking, we would see that this image seems little less exposed, overexposed than even the histogram equalized image. It is interesting to look at the corresponding histograms. So for the histogram equalized image, what we obtain is the histogram of pixel intensities is essentially covering the entire 0 to 255 interval. However, if you look at the histogram of pixel intensities for the image that we obtained out of our fuzzy inference system by applying our fuzzy inference system, this is what you see. Essentially, it is stretching the original histogram of pixel intensities, that is the histogram of pixel intensities of the original image, even though it does not actually extend to the entire interval 0 to 255. Now, this raises an interesting question. If you are only capturing the monotonic nature of the system function, why only this kind of a monotonic function? If you look at it, what is it that we have now obtained? Essentially, this is the given any image. Assume this is your dynamic min and this is your dynamic max. So essentially, this is the range that we are trying to stretch. It could be stretched in a linear fashion, or it could be stretched in a non-linear fashion, where the rate of increase can be different at different parts of the domain, different parts of the pixel intensity domain. But the question is, how do we find in which part we need to increase the rate of increase? Well, what we have done so far is we have found out the dynamic range of the given picture and we have expanded it. But even when you look at the histogram of pixel intensities, we see here, while this is the entire dynamic range, it appears that all the pixel intensities are in fact concentrated in a sub-range or sub-interval of this dynamic range. This becomes even more clear in this picture. While the dynamic range seems to be between say 20 and 220, essentially this seems to be the what we could call as the concentrated dynamic range is effectively in a much smaller interval. So this is your dynamic minimum, this is your dynamic maximum. However, if you see here, most of the pixel intensity values, large number of pixels, most of the pixels, their intensities are within this small subsegment of the dynamic range. Let's call it the concentrated minimum and concentrated maximum. Why not stretch this part aggressively? So while we stretch the dynamic range to 0 to 255, we do not stretch it uniformly. The rate of increase of this monotonic function is not uniform, but it is faster over this concentrated dynamic range. So essentially, the idea is not to just only look at the dynamic range. This is what we did earlier. We took n fuzzy sets on the dynamic range, n fuzzy sets on the 0 to 255 interval, and mapped these as the antecedents and consequence coming from this corresponding fuzzy covers. Instead, why not look at it from this point of view? Take the dynamic range, take the concentrated range. On each of these pieces between DMCM, CM, C capital M and C capital M, D capital M, why not define NL, NC and NR fuzzy sets? Similarly, on the mapped domains on 0 to 255, this mapping can be done in different ways. Perhaps here it is the identity mapping. So essentially DM is mapped to 0 and CM is mapped to 0 plus CM minus DM. Similarly on this side, and this range effectively where most of the pixels are concentrated, that we actually increase or stretch even further. If we use this idea, essentially the same kind of procedure that we followed to build the previous fuzzy inference system will be followed. That means we are going to divide this into NL equispaced intervals, have perhaps triangular fuzzy sets on all of these. So you will have NL plus 1 such fuzzy sets here, and NC plus 1 here, NL, NR plus 1 here. So totally you will have NL plus NC plus NR plus 3 fuzzy sets. Similarly on this side, so you will relate them as antecedents and consequence, and you will have those many fuzzy rules. Load it into the Mamdani fuzzy inference system, choose the operations carefully, and what we will have is perhaps a monotonic function coming out of it. If we apply this, how would those figures look like? Let's look at it. So this is the idea that we have. Let's look at what happens to the image with cars. This is the original image. This is the histogram equalized image. This was the image that we obtained when we tried to take the histogram equalization kind of an approach where we only stretched the dynamic range of the original image. Now when we modified it, that means we also concentrated on the concentrated dynamic range and stretched it monotonically at a faster rate. This is the image that we get. Clearly, using the qualitative nature of the system function, this could be called as the first cut idea, and we have refined this, and you can see that among the 4 images that we have got, In terms of visual quality, perhaps this ranks on top. Now, all of this we have done pretty heuristically. However, we are taking information from the given image itself. So in that sense, it is dynamic. Let's apply this idea to also other images. Let's look at this image. This is the corresponding histogram equalized image. Now, this is the image that we have obtained by applying the Mamdani fuzzy inference system as we have just discussed. That means we not only have the dynamic range but also making use of the concentrated dynamic range of the pixel intensities that are present in this image. Clearly you will see that the third image is far better than the first two images. In fact, if you look at these two areas, the grains here are perhaps standing out at a much greater, finer detail than in the other two images. So if you look at this particular image, the histogram equalized image is this, and what we obtain out of our fuzzy inference system is this. Clearly you can see in some parts of the image, it is the details are much better, the contrast and enhanced is much better than the original or the histogram equalized image. And in this case, it's immediately clear visually that the image processed by our fuzzy inference system is much better than the original or the histogram equalized images. Once again, even in this case, you might notice here that the depth that we have behind the characters is much better from the image obtained by applying the fuzzy inference system. Once again, it is immediately palpable that the third image is far superior than the first two images perhaps. However, we should not leave with the feeling that this fuzzy inference system that we have constructed is better always. Of course, this is only a first cut and a refinement of the first cut. We will see here that in some cases, the histogram equalized image does better than the fuzzy inference system itself, the fuzzy inference system that we have built. Of course, as was said, it was from first principles, a basic heuristic based approach to building the fuzzy inference system. But if you would like to take many more parameters or more factors into consideration, you could build a far better fuzzy inference system which would do a much better enhancement of contrast given a picture. So this was one of the images that we have seen earlier. This is the histogram equalized image, and this is what we would get from a fuzzy inference system. Clearly, the details here are of much better quality than the previous two images, so the earlier two images that are there on the top row. Finally, if you look at this medical scan image, we see that what we obtain from our fuzzy inference system, processed by a fuzzy inference system, seems much better than the original or the histogram equalized image. Especially in the bottom row, the details are much clearer than either of the original or the histogram equalized images. A quick recap of what we have seen in this lecture. We know that a fuzzy inference system approximates a given system function by covering it with overlapping rule patches. Using that idea in the back of our mind, we built a Mamdani fuzzy system using the fuzzy logic toolbox in MATLAB, and we have shown how such a fuzzy system, inference system, could be built for contrast enhancement in a given grayscale image. Along the way, we have seen a practical way, a procedural way of how to pick the most important components to build the fuzzy inference system, essentially identifying the input and output domains and building the fuzzy covers on these two domains and relating them as antecedents and consequence to make the rule base, and finally choosing appropriate operators for the inference mechanism itself. This is what we have seen in the last two lectures. In this lecture, specifically for a particular practical application that we have taken. This application was chosen only so that it is easier to explain and easier to code and also to demonstrate, but there are many more such applications where fuzzy inference systems perform a very decent and often a good job, basically being able to construct a fuzzy inference system from heuristics or the qualitative nature of the system function when other information about the system function may not be available, or exact information about the system function or even data from the system function may not be available to approximate. In the last lecture of this week, we will look at the Takaki-Sugeno-Kan fuzzy systems. You might recall there are two major types of similarity-based reasoning inference schemes. One is the Mamdani fuzzy inference system, which we have discussed at length, both the theoretical aspects and also the implementing and practical application aspects of Mamdani fuzzy inference system. The second major SBR inference scheme is the Takaki-Sugeno-Kan fuzzy system, and this is what we will take up in the next lecture. Glad you could join us for this lecture. Hope to see you soon in the next lecture. Thank you all.